So hi, everyone. Welcome to the Onehouse Meetup with Apachi Hudi. I'm Nadine, and I'm on the DevRel team here at Onehouse. And we're joined with Vinoth and Kyle and some other folks from here from Onehouse. So I'm excited to see you all. And let me go over here. Okay. So for the agenda, we're going to do a couple of updates. We're going to go over the community updates. And then we're going to go over Hudi 101 and Hudi EMR with Suthan. He's here as our guest speaker from EMR, right? Assay. Yeah, EMR team. He's the assay there. And then Vinoth is going to do a vision and product roadmap. And then we're going to have an open forum, Q&A, and more networking. So for the community updates, it's been an exciting month here with Apachi Hudi. We've had over 106 merges, overall pull requests is 73. We've closed 95 issues, and we have 46 new issues. And then you can see all the contributors on the bottom right. And then for the project updates, we have the RFC 64. This is basically the APIs to facilitate the query engine integration, so you can integrate an query engine with Apachi Hudi. And then we also have the RFC 63, which is to improve the query performance by adding a new indexing capability that can effectively prune files for certain types of use cases. And it's basically to improve query performance. And then on the roadmap, we have 12.1 that's coming out. It's just basically like a minor release for bug fixes. And then we have our major release coming out with 13.0, and Vinoth is going to go over more with the roadmap. And then to join the community or get involved with the Apachi Hudi community, you can join our Slack. You can also like and follow our GitHub. That would be amazing. And then if you want to join the Slack, you can scan for the QR code. And then I'm Slack. Huh? And then I'm going to go ahead and pass it to Suthan to do a Hudi 101 and getting started with EMR and best practices using EMR with Hudi. Suthan?
Hello.
Just press this. And go here. Oh.
Hello, I am Suthan Phillips. I'm the big data architect in the Amazon EMR team at AWS. I focus on all the applications which is supported in Amazon EMR product, which means I also get to work on helping customers with Apachi Hudi and other open source implementations. So before starting about Hudi, let me give you a quick overview of the data lake challenges. Customer prefers data lake for when they have a use case where they're ingesting a large amount of data. It's cheaper to store in a data lake, but it has its unique challenges. For example, it doesn't offer transactional support out of the box. And one other thing is the file size management. Hudi, the applications with higher parallelism can create a lot of small files in Amazon S3, and it is expensive. Okay, Amazon it can have a lot of small files in Amazon S3. So if you want to the Hadoop applications which you want to query the data set in data lake like Amazon S3, the small files can be expensive to read. So that's one of the problems. And other thing is, let's say record level upsets and deletes. So in terms of data lake, if you want to update a record, you need to basically download all the files, download the file, update the record, and then I'll upload it back to Amazon S3. So using these are kind of the challenges which customers have a data lake, and Hudi solves all these problems. And let's see about Hudi. Apache Hudi is an open source data management framework. It provides transactional features on top of data lake. So if you see the image, you can see that you can have a data source like a Spark data source or Flink data source, which ingests data to Hudi data to Amazon S3. And when you write it in the Hudi data set, along with the data files, you'll have the index information in Hudi as well as the timeline metadata. So timeline metadata is something that you'll have each action generating certain timeline information like commits, compaction, which you can visit, check it in the .hudi subfolder. And this will help in, let's say you want to roll back to a specific timeline, this timeline information will be helpful. So once you have your data in the Hudi data set, you can use any query engines like Presto, Spark, Hive, or Trino to read it from there. So a quick overview of the table format. So Hudi organizes the files logically into file groups and file sizes. So each file group will have a file ID, and it can have multiple file slices. And this is logical, and you will be able to see the Hudi files in the base path and under the Hudi partitions. Now coming to the point, like why Hudi? So first, with data privacy compliance. So let's say GDPR use cases or CCPA. Hudi helps here by taking the burden of file management, allowing you to simply specify the records that needs to be removed. And Hudi uses this index to only touch those specific files and contain those records. This saves you time and resources and limit the amount of data that needs to be rewritten to satisfy the user's right to be forgotten. And second, consuming real-time data streams and CDC ingestion. So Hudi helps simplify the process of applying changes from streaming data sources and CDC logs by exposing the ability to upset records either using Delta Streamer for no-code solution or using the Spark data source API. And tracking data changes and rollback. So data has to be trusted for it to be useful, and providing a quick way to see all of the commits and activities performed on a data set, see what data has changed since a specific time frame, and roll back a change and revert the data to a save point, and are key benefits you get from Hudi. Lastly, Hudi helps you simplify the file management on Amazon S3. So you simply tell Hudi like what record needs to be upserted or updated or deleted, and Hudi takes care of touching the specific files, updating the record, and or deleting the record in Amazon S3. So let's talk about Amazon EMR Hudi integration. This is a snapshot of the page. I'm showing it from the EMR documentation on the EMR release notes. So you can see here in EMR, each application are snapshots, which means all the applications are locked to a specific version on each release. So you can see here Hudi application, like how we have updated Hudi in each EMR release from 6.6 to 6.7 and 8, like from 10 to 11. And the latest EMR release is 6.9, which is 12.1, which I believe is the latest in the open source community. And Hudi, we install Hudi by default when any of the Hudi supported applications is installed in EMR. And also, we integrate test Hudi with the other application, with the open source applications like what we provide with EMR, like Spark or Hive. And So this takes this takes the burden out of the users just to focus on the application logic and not worry about a dependency on what specific versions Hudi support, what specific versions of Spark or Hive that Hudi latest version is supported to. Moreover, we have a Hudi committers in our Amazon AMR team who work on fixes and features, and we tend to give all this work. We tend to give it to we tend to give it back to the open source. So this is a snapshot of the page which I took from the. Again, I took from the AMR documentation, working with the data set. So as you can see here, we have the Hudi table. We give the table name. We give certain options like the table type, which can be copy on write or merge on read, which we'll see in depth with examples in the next slides. Then we have the record key, which you can think of like a primary key in a database. So record key in Hudi can be unique within a partition or across partitions. And the partition part is the Hudi partition. You give the attribute based from your data set. The precombined field is something that when let's say you have multiple records incoming to your data set, like in the in-flight batch, you have like multiple record keys in the same batch. So based on the precombined field, you tell Hudi to determine which is the latest one to be updated in the storage. Its behavior is customized by the record payload, which we'll see later. And the rest of the configurations is for the Hive sync. It's to sync the metadata to the Hive metastore or glue catalog. With this, I will talk about the best practices in Hudi on how to select each of the options specific to your use cases. So first, we are going to talk about copy and write. So this stores data using exclusive columnar format, which is Parquet. And in copy and write, your incoming batch of like whenever you have an update, it rewrites the base version of the file with the merged records of both the base version as well as the update. So it rewrites the entire base file into a new file which contains the merged records of the updates and the original files. So let's see this with an example. Here at timestamp T1, we write 100 MB of data in partition 1. So here a file group with file ID, a new file ID like, let's say XX here, gets created, and this is logical, and a file slide which T1 with 100 MB of data is created in the partition, Hudi partition. Now timestamp, similarly, like if it's another insert, like we get 90 MB of insert in a new partition, it creates a file group with a new file ID in a new partition. Now let's say we get an update with 1 MB of data. Here, a new file is created in the file group XX, and we have a new Parquet file which contains all the data of the previous file group plus the updates. This behavior will differ in merge on read, which we'll see it shortly. So next, when we get 50 MB of inserts, we see that the base file is again in file group as the Parquet file is rewritten to 120 MB because Hudi maintains a max file size by default of 120 MB, and the remaining 30 MB goes to a newer file group in the same partition. So any subsequent inserts goes into the newer file group until it reaches 120 MB. And then the file groups gets created in the same partition when you get inserts for the same partition. So this is about a timeline, which I showed you in the initial slide, how the timeline gets maintained. So when there is a, right after the insert at T1, we had a commit operation For this, a file was created with, let's say, a file will be created in the timeline with commit requested. Then you will have an in-flight file when the commit. Then after that, you have a commit file being created in the when the write operation is finalized. Now coming to merge on read. This stores data using both columnar format and row-based arrow format. And here, instead of the base file getting rewritten, whenever there are updates, the updates will be logged to Delta files, which will later be compacted to new version of the base columnar files, which we'll see in detail with an example. So here, with the same operations like what we saw in copy and write, we are going to see in merge on read. At timestamp T1, we will write 100 MB of data in partition 1. Here, a file group with identified by file ID access is created, and inside that a file set, which is very similar to what we see in copy and write. And this again, when we have a new insert, again a new file will be created under a new file group in another partition if the insert is for the other partition. Now here the behavior differs. So there we saw whenever there's an update, the base file gets rewritten with the merged version of both base file and incoming updates. But here a log file gets created. So when we have 1 MB of update record, that particular log file gets created there. And again, now when we have new inserts, the behavior changes slightly in merge on read. It creates a new file ID in file group, and it writes there as a base Parquet file in a new file group. Similarly, if there's any other, let's say there's another 20 MB of update, 20 MB of insert record, it writes in a new part, in the same partition, it writes as a new file group. Now, you're getting let's say another update with 10 MB for the file group, for the initial file group, which is XX. So here we see now a new log file getting created, which is of 10 MB. And let's say the Hudi commit inline Delta commits is set to 2 in this case. By default, it's set to 5. So here, if we have set up configuration to 2, this will trigger a compaction operation, which is shown in the slide. So all the 3 files will be compacted, and a new file slice will be created, which is in Parquet format at timestamp T7. So here we see that the timeline information for the same merge on read operation. So there we saw a commit being requested and an in-flight and a commit being created in timeline. Here, similarly, Delta commit will be requested and Delta commit in-flight will be created. And finally, when the operation is finalized, Delta commit timeline will be able to timeline metadata will be able to see. And it has an additional timeline metadata as well, because this has a compaction operation. And when there's a compaction, you will see a compaction requested file being created in the timeline. And then you will have an in-flight. And when that compaction is finalized, you will have a commit timeline metadata created on the Hudi timeline path, which is like the .hudi in the Hudi base path / .hudi. Now understanding, like with an example, how MOR and COW storage type works, let's quickly see the comparison here. So from the write perspective, COW has higher write amplification because new versions of base files are created for every write. MOR doesn't have that. MOR has lower write amplification because updates go to log files. And compaction is required for MOR because it needs to merge that log files to base file, which is not needed for COW. So here, in terms of read part, COW supports snapshot queries and incremental queries. YAML supports snapshot, incremental, and read optimized. So read optimized query. So the read optimized queries will read the data from the last compacted file. So if the data freshness is not great requirement, I mean, if not is not a requirement, if the data freshness is not a requirement, if it's okay to see the last compacted data and you need fastest read, then you probably can use read optimized queries in MOR. So having seen the comparison, now the application part, like when to use COW or MOR. So COW we recommend with tables with lower ingestion rate or use cases without real-time ingestion. And also COW, like if your use cases require freshest data with minimal read latency, because merging cost is already taken care at the right phase. And also COW we recommend for append only workloads where existing data is immutable. That data will not change, but your new records will be added to the new partitions. MOR is recommended for faster ingestion requirements and real-time ingestion cases, and also for bursty write patterns, for example, ingesting bulk random deletes in an upstream database. So because it doesn't have any merge cost for updates during write time. It's also recommended for streaming use cases and kind of mixed use cases for downstream consumers where some are okay with fresher data by paying some additional read cost, and others need faster reads and can compromise some trade-off in data freshness. Now, next we'll see about a key generator. So Hudi uses key generator, which is an implementation to generate record keys and partition path when you specify it in while writing the data. So there are different types of key generators, which I'm going to explain here. So first one is the simple key generator. You can use this key generator if your record key refers to a single column by name, and similarly your partition path also refers to a single column by name. If you have more than one columns, then you can use a complex key generator. And timestamp based key generator is something which you can use if you want to take the benefits of sorry, that's because so timestamp based key generator which you can use if your partition part has timestamp information and you want to Hudi to retrieve that timestamp based information from the partition path. Custom key generator is something if you want to take the benefits of all the other key generators what we discussed, like simple, complex, and timestamp. You can use it. For example, you can have a record key or something like field 1 with simple key generator or field 2 with timestamp, something like that. Yeah. And non-partition key generator is something if your data set is not partitioned the target, you can use that so that Hudi will generate empty partitions for the data set. And pre-combine. This is something which is used to define a field, which Hudi will use to deduplicate a record within the same batch. So as I explained earlier, let's say in incoming batch, you have multiple records with the same record key. Hudi will use pre-combine to determine which record is the latest before writing into the target Hudi data set in storage. This behavior can be customized through custom implementation of the Hudi payload class, which I'll be saying in the next slide. So record payload is defined like how to merge incoming records against a stored old records for updates. So pre-combine is something what we tell Hudi to take the latest record in the in-flight batch. And once Hudi determines the latest record, this record payload is determined how it needs to update the record in storage. I'll explain this with an example. So first one, which is the default, is overwrite with latest Avro payload. In this case, whatever record you get, Hudi will whatever record based on a pre-combined, right? You have an inflight batch which has multiple record keys, and Hudi determine this is the latest record. And whatever record is in the stored in the storage, it doesn't matter. But Hudi will overwrite it with the latest record from the incoming batch. In the default Hudi record payload, it will do a comparison based on the ordering field in storage and determine if it needs to rewrite it or if the data which is already in the storage is the latest record. Let's see this with an example. So in commit 1, let's say you have a Hudi key 1, which is the combination of the partition path and record key. Hudi key 1 has a value 1 and pre-combined 10. And let's say in the in-flight commit 2, you have the same Hudi key with value 2 and pre-combined 5. What happens here is if you use the default override with latest payload, latest Avro payload, the final record in storage will be the value 2 because the pre-combined, it doesn't matter, like it doesn't compare the pre-combined field while writing it when you're using the default one. But if you use default Hudi record payload, the final record will be value 1 because the pre-combine of the already stored record in storage is pre-combined 10, which is greater than 5. Now coming to index. So Hudi uses the index to locate a file group for an update or delete. For the record key, it needs to understand that which is the file group to touch to update or delete the record. So there are two types of indexes in Hudi from a very high level. One is the global index, in which the record key uniqueness needs to be enforced across all the partitions. Another one is the global index, which is the record key uniqueness will be enforced within the partition. Based on this, you have multiple, Hudi has multiple pluggable index implementations. So one is the Bloom index, which is the default, and the information, the index is stored on each data file footer of the Parquet files. The other one is the simple index, which performs a join of incoming delete update records against all the files in the partition. We recommend to use simple index if your updates are spread across all the files and all the partitions. Where, for example, in Bloom index, like if the initial pruning, what it does by comparing the file footer is helpful for a use case, then Bloom index is recommended. But if you have random updates, then you can use simple index. So bucket index, it distributes the record to the buckets using a hash function based on record keys. So it is different from the indexes what we talked about. And it also locates the file group based on the hashing algorithm, what it used to write the records to the buckets. And other index is the HBase index, which we recommend to use. I mean, it's a global index. Recommend to use if your global Bloom index or global simple index for your use case. But for HBase index, you need to manage a separate HBase cluster. So if your use case demands higher performance index lookups, then we recommend HBase index. Hudi community is working on record level index as well. So that's something will be beneficial for global index use cases once it's released. Now coming to the migration guidance, we do have we'll talk about both two options here. One is the bulk insert, and another one is the bootstrapping. So bulk insert is rewriting the entire data. It rewrites the entire data set, and we recommend to use this. And the sort modes can be, there are different sort modes in the bulk index and bulk insert, and it can be configured. So one is the none, And here there's no sorting happens. So this is highly performant option. So, but your records will not be sorted, and you'll get a performance of Spark, like Spark write performance. You should be able to get it using none. In global sort, your records will be sorted across all the Spark partitions. So it will sort the records, and it will sort the records globally, I would say, because it sorts it across all the Spark partitions. In partition sort, it will be sorted within the Spark partitions. So you can use Spark partition if you're already partitioning the data.
It's easy to have fantasies.
But global sort is something
It's easy to have
recommend you
fantasies.
use if you can handle the one.
That's the wish list. Your feature list is a wish list.
On your data set while writing the data.
Right. Don't. Yeah, come.
So these are the two options, configurations.
So
These are the two configurations which you can tune while using the global. Well, I mean, this will impact the write when we use the global sort. So one is the shuffle parallelism, and it's the max file size. Max file size you can keep it to default, which is 120. And the shuffle parallelism, you can set it to based on what is your total data set you're trying to migrate to. So by dividing the total data set size in MB with 120, you will get like a number which you can set it to the shuffle parallelism, so that many amount of files will be returned in that target while using bulk insert. But in reality, it can write slightly more number of files because each Spark partition can be mapped to like more than one Hudi partition. And coming to Bootstrap, we have two modes for the, like if your data set is already in Parquet, there are two modes to use it. One is the metadata only, another is the full record. So metadata only generates record level metadata for each source record while for the source record in data source. So while you're using metadata only, your data will not be copied, but Hudi only writes the metadata on top of your source data. So this is the default mode, and this makes onboarding faster, unlike this.
So,
and full record, here the original data is copied and rewritten with the metadata as Hudi files. So in migration guide, if you're using bootstrapping for a migration, the strategy we recommend, often recommend customers, is to use metadata only for a larger set of full partitions and full record for smaller set of partitions. So let's say, for example, you have 10 years of data, and maybe the most of the reads or querying happens for the last 1 year of data, so which will be the hot partition. Then you can use metadata only mode for the 9 years of data and full record mode for the 1 year of data. So this blog, I have provided a reference here, which gives you the implementation details on how you can implement the strategy, or how you can adopt bootstrapping or test bootstrapping for your use case. And I provided additional resources as well. So one is from our EMA documentation, which provides you sample data sets as well as sample code to work with your data set, to work with Hudi. And the other reference I gave as the best practice blog, which we recently released. This covers the options which will help you, discovers the details which will help you to determine what option you need to have what option you can optimally select for if you're building your Apache Hudi data lake on AWS. And part two, the other part, this is a series, and other part will be released soon, which will have the details on the optimizations and also on how to monitor your workload so that you can optimally use it. With this, I will hand over to Vinoth.
All right. I think that was like a super detailed presentation. Thanks, Suthan. It was a very interesting blog as well. All right. So everybody can hear, right? I mean, of course, here, but all right, cool. So next 30 minutes or so, I'll try to take you through the Hudi vision, the roadmap, what's going on. And I'm Vinod. I also serve as the PMC chair for Hudi. We originally created the project while I was at Uber. Most recently, I'm also founder CEO at Onehouse. And in Hudi, I think
So when it is done, and Rock says no.
somebody not muted. Right. Cool. All right. So I like to joke that Hudi is still like super grassroots open source community. So just as a disclaimer, right? This is my summary of kind of the different efforts going on in the community and what I think is going to go right. And I merely take credit for all the other good work that the community actually does. So I'll try to summarize by starting out in what we did in this year, like what shipped out, what's going to ship in 0.13. We'll talk about what does 1.0 mean for us, what is our path towards that, how are we thinking about releases going forward. And then also, sort of like, what are we building towards? Like, why are we like, where did we start? Why did we start the project? Where are we now? Just to do a checkpoint and see some of the things that we plan to like build. And these you can find in on the site, you can find like a large manifesto which goes over a lot of these things. So I'll try to summarize and put things into perspective. All right, first things first, we had like a pretty awesome year again. We had like way more issues and PRs and all this merged across the community. And I think we've added about like 120 or 140 more contributors to the project. We are over 350 contributors right now at the project, which is kind of like really awesome, and also places a large responsibility on the PMC to kind of like make sure a lot more people can contribute to the project and we can scale processes and stuff. So we actually done a lot of work around this year, including work with the EMR team to make sure we can release very easily, like, as long as the open source is released. Right. Cool. And yeah, just to kick off what Hudi is, right? So we describe Hudi as like a platform. So essentially the way with kind of like three different parts to it. One is the thing that you'd have heard a lot about when people talk about like table format, transactions, and all of those things. It's like a core set which gives you, better ways to store schemas and metadata and a bunch of table services that operate on the table, concurrency control, and indexes, which I think Slang just covered. Right. On top of that, we expose like readers and writers, SQL and programmatic access from different engines, and mostly Java at this point, but I'll talk about what we plan to do next year on that. And at the very top, there's a whole bunch of platform services that we built on this stack. Like starting from like a streaming ingest service, commit validator, data quality checks, and like we sync to about like 6-7 meta stores at this point now, where you can have like one physical copy of the data and then use it to sort of like run your data lake. So Hudi is really imagined as think of the data lake or the transactional data lake as a database. We are the bottom half of it, right? And then the top half, you should be able to fit any engine on top of it, and then get the price performance as you decide. And then obviously there's a whole bunch of SQL engine integration on the right. And that's the link to the full manifesto. I think it's linked also on the homepage of Hudi as our vision. So again, it's a 20-page, half-an-hour read. So, all right. So this year we shipped out like 2 major releases, and I think we'll probably like code freeze 0.13 before the end of the year in December. So some few highlights, right? One is multi-model indexing. Essentially we generalized metadata and stats instead of like thinking about it in a more of like how do I track stats on the table, we kind of made it into a generic indexing subsystem where we can actually store Bloom filters like record indexes. And I'll talk about various kinds of indexing systems that are built in by the community out there. And then we implemented data skipping that's now available for Spark, and new kinds of indexes like bucketed index, schema evolution, support what we call schema on read, which is allowing you to do more of these like backwards incompatible schema changes, and a bunch of like, things out there, and probably added a bunch of source connectors as well to our Delta Streamer ingest tool that I haven't covered here. And point 12, I think the main focus there was getting Presto and Trino dedicated Hudi connectors. So Hudi also has support for reading through the Hive connector historically, and we've added brand new connectors now, and a lot of development is actively going on these like new connectors. And then we have like, added Bloom indexes to our metadata table. If you're familiar with DBT is like a fast growing tool out there to build data pipelines and sort of like SQL-based EDLs. We added support for DBT. Spark ships with the pre-built support for Hudi. And yeah, I think point 12, we focused a whole bunch on performance and general SQL improvements. It was more like a, like a performance release where you probably don't see a lot of features, but actually under the hood, we've rewritten a lot of code, and we've like made things like a lot more performant. And point 3, then we like actually have a bunch of exciting features now, where there's a record key-based index, and like I'll talk about it a little bit more. There's a new CDC format. Hudi has had incremental queries for a while, but we're introducing a Debezium or like a database changelog type. Like if you're familiar, if you're as old as me in the database kind of like field, and things like Golden Gate or in these more CDC tools, we've standardized a CDC format, which is very similar to those sort of things. And we have log compaction. We are actually lower part. We are introducing newer APIs for merges and tables, and just like working with the Hudi tables. This is actually probably the biggest change that we've done to Hudi APIs for a long time. We are actually rewriting some of these things to make it easier for newer engines to sort of adapt and sit on top of like Hudi. And we're doing a bunch of things around like eager detection of conflicts so that we can give back more of the cluster time back. If let's say, 2 transactions are going to definitely conflict, how can we, abort that early and then give time back? These are a bunch of things that we're doing. The next set of slides, I'll go over some of these in a little bit more detail. And feel free to actually also like, if you're completely, just feel free to ask questions as well as you go. Yeah, first thing, like I mentioned, right, multi-model indexing. So the idea here is there's the data table that you actually see, which is the Parquet table, right? We've actually stored typical to how databases do it, or there's an internal table which now stores all kinds of different metadata about the base table, and these two are transactionally updated. They're kept in sync with one another, and there are many types of different indexes that you have. And then we also built out like async indexing mechanism. I see if you're in the EMR talk earlier today, you probably heard about this as well, which is you can build these indexes in parallel. So think of it as like how we would interact with like Postgres or MySQL. You go build an index, the indexer keeps running, and then you don't have to take your queries offline or the database offline. So we built out a lot of foundations and the concurrency control and the protocol that's required to do something like this. And data skipping for Spark. So what's kind of like very innovative about this, right? So here's the deal. So if you just take, we looked at how data skipping is done overall, and this is why we call it more indexing, right? Just think of this at 1 TB table, right? And you want to store 16 MB files, and you can obviously play with these numbers, but you have a table with 100 columns, then you have 6.5 million stat entries. If you want to actually store that in an Avro file or a Parquet file, just as an example, you'll just need tens of seconds just to read that metadata. So while all these current approaches out there do help you solve S3 throttling issues or like file listing overheads and stuff like this, but they are by no means like kind of ideal, right? So what if in real world, you'll probably have like 100 columns is more like your TPCDS style, like, like toy workload, right? Like your real data, if you're ingesting a lot of JSON, you probably have nested schema, you have like thousands of columns, you have at least like, a couple hundred columns. Then just this metadata, managing it in like plain flat files is like very costly. So we actually leverage the fact that cloud storage cloud storage systems support range reads, right? And then so we actually build an indexed way to encode the stats for every file, where you can see these numbers, where we can actually we use H files to do our thing. That is like row 4. We can actually do this in like 1.7 seconds, something that takes, let's say, 26 seconds to do in like Avro-based, Parquet-based kind of like systems, right? So this can also now scale with the number of columns in the queries. Let's say you have 1,000 column wide table, and then your query only supports, only reads like 10 columns. That's typical, right? So you don't have to read the entire Avro file because it's an index file. You only read the stats for those columns that are actually in your query. So this shipped out, and then, like it's available as part of Spark, and it's being integrated into Trino and Presto. You can follow this RFC for more details on this. And bucketed index. So like Hudi comes with, like, I think Suthan explained, right? Like a bunch of different indexing mechanisms. Why is there so many indexes? But you can look at any database. There are like many indexes because each one is good for different kind of workloads. And databases usually hide it and the optimizer will pick it for you. But, here we are like in data lake land, we are learning to crawl now, right? So we'll be running in like a year. So, but for now, right, we introduce a new, something called a bucketed index, where let's say your data doesn't have any temporal locality, you want to go very quickly, go update, just log all updates to like a MOR delta table, delta log or something. It helps you really do that. And point 13 actually adds a very cool consistent hashing based technique for shrinking and expanding these file groups, because sometimes you start with too little parallelism and then the writes take long time. Then, okay, how do you change this, right? So what I described there is like some way to do this kind of like constant hash based shrinking and using like a, like a clustering as a clustering strategy in Hudi. This I covered already. Presto has now support through the Hive connector. There's still like a lot of conversations in the Presto community around what's the right way for all these different like table formats, transactional like data lake projects to be integrated, because Facebook and other companies are still contributing very heavily to Presto and into the Hive connector. But for now, Hudi is queryable. Is performance optimized through file listing and all of these things through the Hive connector. But we also have a separate Hudi connector now, which is actively maintained, where we are doing a lot of these new indexes are being exposed to the queries as we go. Trino, we just added like, there's a support through Hive, but it's not been optimized. It hasn't had the fixes that are in Presto. So the new Hudi connector is the way to go. And it already integrates with all these like metadata file listing sort of things. So there's active work involved on both sides to, sort of like both engines to bring MO snapshot queries, incremental queries, and all of this other stuff going on. All right. So this I quickly touched on. So the main difference was Hudi has had incremental queries since version 1, like even before open sourcing, or even when the project was created at Uber. But it only gave you like soft deletes and updates and inserts. So there are like a lot of use cases where people wanted hard deletes and, sort of like, oh, give me both the before and after image. So what we really did with this project was we actually, now Hudi gives you like a before and after image, also propagates the operation field, which is very friendly to systems like Flink, where they can actually take these as a stream and then update downstream, build a downstream representation of the table as well. And we've done a lot of work here because I think the Spark batch ETL use case is very different from the Flink thing. So there's like actually a lot of debate in the community around this. We've now actually made it more tunable, like supplemental logging. What we really mean is like you can control how much overhead you want to take when you want to enable changelog, right? Because if you want to record every like, for every write, you want to record a previous image, then you effectively have to write 2 times, right? So you can control whether you want to write 2 times or dynamically compute on the fly. So this is what databases do. If you look at something like Oracle, this is called supplemental logging. And then you control like kind of like how much you want to log and how much you want to like compute on the fly. So we've done this thing now. It's going to ship out in 0.13 as well. And yeah, this is like a really exciting project. And this is actually pretty, the idea is actually as old as Hudi itself, honestly. So like the many different workloads, update workloads, Hudi can do most of them really well. What is the one thing that tests Hudi a lot, and like any database a lot, is a global indexing use case with completely random writes, right? Because essentially that is very hard. You have a lot of records coming in, and you need to essentially figure out across a large number of partitions where this should go, right? Which file has this particular record. It's a very hard problem, as you can imagine. And Hudi has had like this HBase index, which uses like an external key value store to solve this problem. It's fast, but then sometimes, you need a additional operational overhead to operate that thing, right? So now essentially HBase index was originally built while I was at Uber, and then we had to solve this use case this way. Now I think like, this operational overhead of running HBase, and then so the Uber's engineering team is actually building a record level index within Hudi itself, built actually moving away from H files, but using HBase, but using the H file format. And it's now being tested for like, a single table as like a 13 terabyte index. So it's like, a very, really, really large, multiple 100 billions of records. We're really trying to harden this. And then we want to really get this out into 0.13. And then once this is out, I think I see a lot of use cases in the community where people have large dimension tables. I was literally talking to somebody here today about large updates going like many years in the past and spanning multiple partitions. All these kind of random use cases, Hudi is like be like super, super fast. Right. And we also built out this thing called log compaction. So right now, one of the things with MOR, the MOR is like, there's a base file, and then there's a bunch of logs, and then you always merge the base against the log, right? But sometimes the base file is, let's say 2 gig, and then the log is small, right? So what do? So we build a log compaction where you can take a part of the log and compact it. That way it further cuts down the cost of like merging. So this is also shipping out in 0.13. And finally, there's a lot of like newer APIs that we're pulling up just to make sure that the newer query engine integrations can go smoothly. And the first one is, I don't know if you can read, but so we are introducing a new replacement for record payload called the record merger API, which is going to be essentially, it moves away from Avro as the canonical kind of like data representation to supporting more engine specific ones. We still support, will Avro fall back to the record payload for backwards compatibility, but this unlocks things like you can now use Spark Row or Flink Row or engine specific Pojo to actually implement these base log file merges, which can avoid like like a format conversion, and it can be like really fast. So right now Hudi is already fast on the merging because we for every base file we bound the amount of data that you're merging, right? So that with the indexing, it gives us like that's why it makes it like the merging very like actually feasible and practical to do. But this will like further speed it up with this and the log compaction. These things are going to speed up like MOR snapshot queries by a lot. And we also put out like a tech spec. This is like kind of funny that we usually are lumped together with like a format kind of, okay, here's another table format, but we actually never do Hudi as a format. We'll talk about this in a little bit, but now we are actually like, we put out like a table spec, and we are now publishing first class Java table APIs for easily okay, here is some metadata. Okay, these are the 4 classes imported, like it'll give you metadata. Here is like a file, it's a way to read like a file slice. If you want to read that, here's a file slice reader, file slice writer. So standard APIs are coming. That way, any Java-based engine should be able to integrate Hudi very easily. So there's like a lot of like asked for, let's say, for example, writing from Presto or Trino, for example, can be implemented very well using something like this. And once we have that next year, I think we can take that as a blueprint and do more Python, Rust, and all these things. And here's where I think we kind of like expect more community contributions as well. But as it comes, we're going to invest in most of these bindings as well. All right, so this one, I think actually the EMR team is driving this. So this is an effort to sort of completely decouple physical storage from kind of logically how you view the table. Okay, here's a table and here is a bunch of files, right? I've color coded them here. And then we are introducing like a new Hudi storage provider layer where you can now like sort of like take piece of files, place it in different buckets or even within the bucket distributed across different random prefixes to overcome throttling. So we've tried to take a more holistic approach here, try to deal with issues like, some people want, they have like SaaS companies who want customer data in different buckets encrypted in a different way. We want to support all kinds of these use cases. So we're trying to build like a more federated kind of like way to distribute this. And we'll still support the default way. I was literally talking to Harsha here, who was like, no, I want the file folder based partition that's like readable. I can understand where each data is. We'll still support that, but we're adding this as an additional sort of thing. So the nice thing, so if you wink a little bit, right, like in squint and look at it, what we're really trying to do here is we're trying to take this more towards like how, let's say, like again, databases or RDBMSs manage data underneath. You really don't know, like actually, like how the individual physical files are laid out by InnoDB, like MySQL or something, right? They usually manage internally by the database system. We're moving towards that model. So how do queries get speed up? Because like, you have a partitioning scheme, then when you write a query, then queries can take advantage of that, right? So the answer to that is this new thing that we are working on called index functions. So just like how, again, drawing the database analogy, in a database, they usually has pre-built functions where you can write, select star from table where some function of some column equal to something, the data, as long as it's built in, that like the database is smart enough to actually build reverse mappings to actually figure out and index like a function of a column, right? So we're building these out as first-class APIs, probably will get integrated into Spark or Presto, one of those engines first. But with these, what we really get is we'll completely move away from this notion of partitioning. This is like a super, like instead of hiding them or like specking them out or whatever, just like get rid of partitioning altogether, just treat it like a database table and just solve indexing. I think partitioning is just like a very roundabout way of solving the indexing problem. So we're just like trying to just make it like simple, like a database, so that it's actually, and overall, I feel like this will make data lakes much easier to understand for, let's say, a large amount of backend developers out there as well. All right, how are we thinking about 1.0? So here is the main thing that we heard is that we moved pretty fast. So we need like some LTS support version. So 0.12 is going to be that. We're going to continue doing 0.12.2, 12.3, essentially there's actually a lot of Hudi users who are on like much older versions as well, right? So we'll try to get them on to like 0.12. This should give you all your stock data lake features. If you just want like, do updates, transactionally update a table, this kind of thing, like, you should be able to get on this version, like really get good, Spark experience, right? And as we build these new features, we're going to go towards the next 0.x versions here, like I talked about. And then we'll have like a 1.0 milestone release when all the storage format and the building blocks at the storage level that we need for the next part that I'm going to talk about, which is our like more forward-facing vision, is actually in place, right? Then we basically can provide, just like how we maintain backwards compatibility on 0x for like, like 3 years now, right? We want to make sure once we go to 1.0, there may be like some migration effort that may be involved to go from a 0.x to a 1.1 major release. But then once we are there, we want to make sure the new stuff that we are going to build all is like backwards compatible, right? So that is the checkpoint for us to say, okay, this is like 1.0, and like anything that we need to build now, it's like can be supported, right? That includes most of what I just talked about, right? All right, anything so far? All right, cool. Let's check on time. All right. So, all right, let's do a quick check on why we, like, at least for me, right? Why we even started this project to begin with, right? It's actually around, this is the original idea, right? Behind Hudi when we started Uber. On the left, we had, okay, we had a database, a simple example. We could actually, like, you could do change capture, get it into like some system like Kafka. And now how do we apply it? Like, we actually ingested it, bulk ingested 120 terabytes, right? Everybody else wrote batch jobs. The actual change was only less than 500 GB, right? Then we still do downstream ETLs, which had no idea what has actually happened. The ingest would have actually failed for like 16 hours and the damn thing would still run, right? And if you guys are familiar with Jan at Uber, for a while, I was Jan. Like I know what order to kill these jobs to recover the damn thing, right? So we were like, this madness, right? There's no intelligence whatsoever because none of these computations are really chained in a very intelligent sort of way, right? So this is how we started. We didn't start by like trying to create a standard format or anything like this. We always thought about it as a database problem. Maybe because I'm biased because I worked on databases that way. So, we wanted to solve terrible ingest problems, low expensive recomputations, right? And then on massive data volumes, right? So we essentially thought, can we bring like, well, where have we solved this? Stream processing, we've solved this already, right? Before Uber, I was literally at LinkedIn where we did like all this Kafka thing, right? So, then can we bring these concepts to the data lake? That's kind of like how the project got started. So we went from on the left to a file-based data lake to what is now like a transactional data lake where, we can go take these up, like build updates, apply it less than 10 minutes. That's why Hudi has like record keys and like, it's really optimized out of the box for like updates, right? And then going back to my earlier comment, right? This is why we had incremental queries from day one, because we had to build this downstream table and actually build like an end-to-end model, like a warehouse table within an hour, right? Overall, and this ETL can be complex, right? It can be simple, it can be complex, it kind of like varies. And this is kind of like these original cases, I think even more valid now. I think back then when we tried it, a lot of these frameworks didn't even have good support for this kind of thing. Like there's like Beam coming up, Spark structure streaming was barely there, like Flink was just growing, right? And that was on the left is the original blog that we wrote in 2016. It'd be like, why is everything so batchy in the kind of like the Hadoop world? And then I think this is like 2019 where like, Jay is talking about, well, like all these warehousing ETLs, merge statements that you're writing, they're actually reinventing stream processing in a very like slow way, right? So now I think most of what we've been talking about is how do we make this faster and more error, like, less error prone. What do we do? I think you all understand this, right? Like there's a dichotomy out there today. Like you do stream processing with a stack like that, where you do like Spark streaming, Flink, get it into something Elasticsearch and server analytics. It's intelligent incremental because you only consume new data and then you update your existing results. And it's fast and efficient because of that. But it's all row oriented. It's not scan optimized. It's like it's purpose-built systems, right? For this purpose. And it's always like a separate thing that you build on the side. But the same data usually gets into the so-called the batch land, where you have Parquet, you have like all these transactional formats now, and you can do a bunch of like batch jobs, scalable compute. Like look at how good, like let's say like something like EMR, Spark, and all these compute things have gotten. You can do a lot of processing power in your hand. but it's like the same thing, right? It's a lot of like inefficient recompute even today. And well, no updates in the is not really true. I think he copy pasted something. So this is where we started, right? Like we said, okay, here is something called incremental processing. We took the incremental part of stream processing. We're still not running long-running containers, right? We're just doing things incrementally, that's all. Our argument is just by doing this, you can gain a lot more efficiency in whatever you're doing today on the batch stack, right? And we actually build transaction updates, deletes, everything for this vision. And if I now check myself on, okay, where are we, right? What have we really done? What have we really accomplished? I think, honestly, when we started on this, people were very skeptical. Oh, you can do like minute level latency on the lake. It was like hours, right? It's not a thing that to do that. And then for a while, even when we open source a project, we thought we were the only like, like a snowflake, like no pun intended, like, doing this kind of thing, like, because Uber is like, so like such a unique thing. But actually now, if you look at it, there's so many large companies who've done this. And this is the great thing about like Hudi's success out there for me. Having as somebody who's invested like every single, like, every day, like brush my teeth and think about Hudi, like this is what keeps me going. Because like, look at this is not some format problem. This is like data integration being done from operational systems into a downstream lake in like near real time. And we've done like a lot of like all this table management that we've built has a lot of warehousing wins. Now there's like a credible warehouse that you can build on top of like a lake because you brought mergers and all these like warehousing primitives to the lake now, right? And then that's like, that shows in like our contributor growth over time. As you can see, there is a GitHub contributors. That is like the membership on our Slack, and like, we have pre-installed on many public clouds now. So it's like validated pretty much that, and nobody's now talking about, no, I'll only do batch ingest, right? That's not a thing that people say anymore. So that's, I think I'll take that as a win. And I think this is what we've done so far, I would say, right? This is like incrementalize the ingestion part. We have best-in-class table management now, like these kind of like advanced techniques like clustering, Z-ordering. We actually brought them in open source for the very first time in Hudi. And like even now, indexing system, we'll see how many people talk about indexing steer. Like, just joking. So like we are like continuously pushing the boundary for what data lake storage ought to be. And we can now write like simple incremental ETLs on the lake, right? And we can do these warehouse merges, these kind of merge statements, you can now write at scale. That's what we've done. But we're still not done, right? So like, what about 30-second commit SLA? Like a lot of issues crock. Once you start to go into like, few seconds, tens of seconds, right? We'll always stay in that like land. I don't think we'll ever try to approach like a sub-second or like anything, right? But even if you want to operate here, the thing is, these are tough write patterns. You're going to dirty a lot of metadata, a lot of data very quickly. And, you have to like, a lot more things come into play, right? That can mess up with your SLA. And what about the reality of the data, that the data is not static, right? It's not like slow changing. Like a lot of these data are like actually fast changing data, right? They can be late arriving data, data skews. Like how do you deal with all of this while still doing that? And what if you want to write arbitrarily complex ETLs, right? Stream joins are notoriously hard. Windowing support, right? If you want to compute something more incrementally, then you need to support windowing. Like, and then what about efficient for triggering these ETLs? I think this is the bulk of sort of like our, like what we plan to build going forward. We want to like take this end-to-end technical vision to completion in the project. And then these are the, I think, the 4 building blocks that we need. One is we need like an indexing subsystem, which kind of that's where we're laying out a lot of the groundwork for. And we need this to like, okay, you can do fast updates, but you can also speed up joins using this. For example, you have like a transaction or an order or something like that, then they change at different points if you want to like join them together, right? So if you had like an index, you need not scan the entire table. You can like, join them very efficiently. So you need things like that. And then in caching and meta server, we need to introduce caching, and I'll talk about it in a little bit, and different concurrency control mechanisms. So there's a blog that we wrote around this. A lot of the current talk is like, oh, it's like a database, but yeah, it's a database layer, but the problem is a throughput problem still. Like it's not a latency problem. So you need to treat it like stream processing systems don't take locks. That's why you get great throughput from like Flink or all of these things. So you need actually approach even concurrency control into like a different way as to how, stream processing systems deal with like event logs and like full API support, right? Like incremental SQL, like windowing, triggering, the whole thing. And we actually did like a limited version of this. The Uber team has actually done this, right? And then this is kind of like what they were able to achieve. But this is not in a like a very generalized way yet, right? This needed some knowledge about the data set and like the heuristics and design these watermarks and all of that, but still like, very impressive benefits over batch processing, I would say. And just to quickly touch upon these parts, right? You need a meta server because you need to be able to plan queries in milliseconds if you want to. Like most warehouses have some like this, like I showed you, even 1.7 seconds with the H file thing. If you want to now write a 10 table query, you're going to spend like 17 seconds just like reading metadata, right? Like that is not a thing, right? You need, if you want to do like really fast queries on this data. And yeah, so there's like actually a bunch of independent efforts going on, and we actually have a like a meta server of sorts within the project that we use to kind of like run in the Spark driver today. And you can see, right, just file listing, S3 baseline. S3 is usually fast until you have a lot of files, and then like file-based metadata gives you like more stable performance at large scale. But look at that thing called timeline server, right? It can do 90,000 queries per second at 1 to 10 milliseconds, right? So so we want to build like a hybrid architecture here where for really fast queries, you can go through the meta server and then actually plan queries really fast. But you should be able to also write your Spark job for your regular batch workload, just hit the usual like, Hudi metadata table and stuff. And the other thing is caching. So if you do faster commits, like I mentioned, you're going to write smaller objects, which means like you're going to stitch a lot of small things together, right? Which is not like a fun thing. And if you usually have fast writes, you also want to query faster, right? So there's this thing called run conjecture, which is like kind of like a cap theorem like thing, where essentially it says you need to pick 2 out of read, update, or memory. Essentially, you need to trade off. You want to write something really fast, update something really fast, and then also read it very fast. At least you need to pay the cost of memory. Because memory can absorb those updates because it's like, you can do random updates, right? So essentially, there are a bunch of caching solutions out there, but where they fall short is they don't respect transactional boundaries. They are not good with, actually mutability. You can't update the cache. It's more like a static block level cache of stuff. And then they're not columnar in a lot of cases, right? You need to, so if you want to, like things like Arrow do a good job of representing the columnar metadata. So you'll have like a hodgepodge of things now. So things that are good at the columnar in memory thing are not good at the transactional mutable thing. Things that can do mutable don't do the other thing. So I think this is where there is like, if you look at Hudi's design, if you can now take a file group and then like keep a compacted version of that in memory, it's actually a very simple operation for us to build. And then it's Hudi's like purpose built for something like that. So this will actually think of this as like your continuing the database analogy that I've been using on Hudi. Think of this as your buffer cache or your database buffer pool for the like for Hudi, right? So that's something that we need to build. And then again, like indexing, this shows like how we plan to. This is from the Lucene RFC. So how we can add more indexes, change query plans, and there's like a whole bunch of things that we can do over indexing. And yeah, this I think I covered this a little bit, but I'll touch upon the last 2 points. So this whole thing about incremental processing is kind of like moot if we still run long-running containers. Like we're always streaming with even no data around, right? Because we'll only be as like costly as the existing streaming applications. So we need like a little bit of more intelligent runtime here. If you look at Hudi's Delta Streamer, this continuous mode thing that I think like, I think Balaji wrote some of it. So essentially you have one Spark cluster, which is long running. So it's long running so that you don't have to keep, creating a EMR cluster or a Yarn like Spark job, and you don't pay that cost of starting it up. It's one, but internally we use Spark job pools to manage the resourcing between writing, clustering, compaction, background activity, and that way. So we have to build a little bit more. Right now, even in Flink, if you look at it, there's only one runtime. Is a batch runtime or there's a streaming runtime. So I don't know what the answer clearly here is, but I think point is this is one challenge that needs to be solved. And the other thing is this is again like a real RFC from like an insurance like industry user, right? Where they're essentially saying, oh, we need two pre-combined event time fields, right? To merge by, because we have like complex scenarios of partial updates, multi-field mergers, event time. So we need to make sure the things like record merger and these lower abstractions can support these kind of complex things. The real world is like a lot different than like, just plain SQL mergers, right? Like that you're writing. So that's pretty much what it is. I think if we get the 1.0 with this foundation and then build these newer components, I think we can build something where we can do end-to-end incremental, like operation system, incremental ingest, incremental ETL, and then maybe even reverse stream it back incrementally out. I think they call it reverse ETL now, I think. So yeah, that's the overall grand vision for Hudi. We're halfway there, I think. All right.
Wow, it's a quiet room, no Q&A.
No questions? That cannot be clear.
So, as a new Hudi user, what determines the file groups, contents, and size? It's hashing that it goes into something that kind of a little bit of slice the table. And how does that relate to say partition keys?
Right. It's a good question.
Do you want to repeat it for the mic too?
Oh yeah. So the question is, what determines the file group size in Hudi, and then how does it interplay with partition keys, right?
Not like size, but like the contents. How do I determine how many file groups there are? How do I determine which keys or which records matter to the file group?
Okay, got it. So, all right. So how many file groups there are? So that is determined by a file sizing number that you said. You say, I want 100 MB Parquet files. Hudi will ensure that there are 100 MB Parquet files. So during the write, it will make sure that it knows the existing size of the existing file groups, and it will expand. Let's say, for example, even if it's an insert, it's going to expand it pack it into an existing file group, which is smaller, just to fill that size. So it does this bin packing automatically. So that also answers the second part of your question, which is like, the file group that your originally record gets assigned to is either determined because of file sizing, or in the normal kind of scenario, or in case of like bucketing, like, the hashing function and all of those determine that. And then once we do the mapping, it never changes. There's a deterministic one-on-one mapping between a key and a file ID that it belongs to. This is like a very significant design difference, because what it allows us to do is we bound the amount of data that you merge. So that's enough. And to complete the answer, only things like clustering can change that. Clustering will basically say, oh, I have these 10 file groups, which are all 10 MB in size. Maybe like, you started with a 10 MB file. Now you want 100 MB, right? So it's going to basically like, merge all of them and then make a new file group. And then this is going to be atomic on the timeline as well.
I have a comment on this. Do you find the size of the file still relevant to S3 being stored mechanism of choice? Like 100 negative file, 100 negative file, tiny S3 file. Do you find it still kind of a relevant choice for Hudi, or is it kind of like an APFS artifact that you want to kind of outside of the file? Right. So S3 or cloud storage system. So, okay, sorry. The question is file sizing still relevant in the cloud, right? So I think yes, it is, because it still largely controls your query performance. So cloud storage systems don't have this HDFS name node problem and all those things.
You're probably asking this because that's usually what gets written when you talk about small file problem. But I have plenty of users who kind of like partition the table super granular, right? And then you end up with very small files. And the thing is, even with all these metadata layers and everything built out, you still need to make n number of calls to actually read, right? You need the get calls. No, you can eliminate the list calls maybe in S3, but you have to actually read the file to actually serve the query. There, I think the file size matters, because even for a single file, right, compression is better if you pack more. And again, like you amortize Parquet has page level stats, right? All of these systems only store file level stats. So once you read an object, right, within that, the Parquet readers do a lot more pruning based on the file's internal stats. So all of those things, if you think about it, if you have a decent sized file, the metadata to data ratio is healthy, and then you can get really good query performance. Otherwise, this extra metadata work of actually reading the Parquet file is a lot. And I think this gets lost. It's a great question, by the way. Like, this gets lost usually in this whole thing where we say, oh, we solved the data lake metadata problem. Yeah, we have, but the point is still a lot of things go on when you read a Parquet file. There's plenty of, and one of the reasons why we designed Hudi's metadata to be like indexed and sort of like deal with larger metadata is one day we hope to be able to move like page level, kind of like these kinds of more granular stats into the metadata table as well. That's why we kind of like, that's what we anticipate, but hasn't really come up yet.
Just to follow up on that, any reason why your default pricing time is 2020? And what are the pitfalls if you grow it even larger? Let's say you want to large, small number of even larger files.
So the question is, why is 100 MB a good initial file size? Under 128 MB. No good reason, except I didn't really feel like on cloud you needed to be 1 gig. The problem with 1 gig is that query performance wise, the query engines will split the file into splits, and that's fine. But on the write, let's say copy and write, you have to, your unit of work is 1 GB. So you have more chances of ooming, you have more chance of like other things going on, right? Let's say you get like a 1 gig file and most of the records are updated. Then maybe like when you like actually update the thing, then you get more chance of ooms, things like that. So there's no particular reason for 128 MB, could have been 64 as well. But it consciously try to move away from like very large file sizes. 120, 100, 128, this came out because that's what we benchmarked back at the day Uber as some like the amount of time it takes with all the variability to write like a Parquet version of Parquet file, because that was our SLA, right? We could do that in a minute. So then we know that, okay, yeah, if your write pattern affects X number of files, you need to give it X Spark executors. Then, just work out the queuing in your head, and then you know what SLA you can guarantee. That's kind of like the math.
Just following up on that, on the metadata server, we spoke about the last part. Is that an infrastructure that will have to be running? And you talk about that, like having it stored by DB and then bringing up those higher level Parquet files statistics, using those services and kind of staying serverless. And I think that brings a lot of advantages rather than having a single metadata service that you have to continue to keep available.
Right. So the question is more on what are the design trade-offs around like the meta server and how we're planning to do that. Yeah, again, great point. I think if you look at Hudi, one of the reasons why it has a lot of knobs is that we try to leave a lot of things pluggable to customize. So in that vein, yeah, ideally this metadata sits in like a key value store, like more maybe like some geographically distributed, like cross-region atomic thing like Spanner. I don't know if AWS has anything like that. I apologize. So something like that, right? Or it can even be like there's a case to be made that it can be just like local RocksDB, because end of the day, the source of truth is the metadata table in Hudi, right? So and for example, we're not going to be able to move Bloom filters out of S3 into the metadata service or into DynamoDB. That's not a good idea, right? So same thing for Lucene indexes, all these other things. So it may be okay to keep like like a local RocksDB kind of instance and index the stats in many different ways. We can build zone maps, interval trees, and like many advanced data structures, which can give you like really fast pruning of the queries, right? Yeah, and in that case, for example, it still be like it is stateful, but it can recover on its own, right? So there are ways to build it, ways to replicate it, like build HA into it. All of these have to go on into the final thing. Right now, the meta server, TikTok's running something in production, which they are upstreaming, and we are working to make sure it gets landed first in open source community in like a like a really good way. This is something that they're already deploying in production to scale out their Hive story that it does like a Hudi specific functionality. So yeah. All right. I'm game, but like anybody has any other questions? Like
Uh, hi. Actually, you have mentioned Hudi supports different file formats as well, right? What does it mean?
sorry, oh here. Sorry, can you repeat that? I didn't catch you.
Yeah, actually, you have like there was one of the slides you have mentioned it supports multiple file format. What does it mean actually?
Oh, it means you can use multiple file formats as base log file formats like Parquet, ORC, H file. These are some file format. Sorry, that we support.
Okay. And it's actually like we're kind of looking for the solution like from like migrating the entire ORC data to Parquet using through Hudi. Is it doable or?
So yeah, so for the room, the question is like, can we migrate an entire ORC data into Parquet? So right now, the bootstrapping mechanism doesn't really allow for hybrid files to exist in the table. So but you can do one of these like bulk insert, sort, mode thingies. And honestly, so here is the like backstory around this. The first thing that we built when we had like Hudi in EMR was the bootstrap feature, and probably did not get used as much because what we found out was most people are happy rewriting the data because Hudi will size the files for you, because they were usually coming from like a very poorly sized files that they were not getting good performance anyway. So most of me ended up rewriting the data, because as the global sort mode that Suthan pointed out, it'll minimize the amount of files in the table while dealing with skews and stuff. So that's kind of like what most people do. You can try the same thing.
Okay, got it. Thank you.
Any other questions? Right.
So growing up like Rust and Python out there, how have you found architectures that you would lead format, say like the use of HBase files, especially secular versus later on?
Yeah, so I don't think so. The question here is there's no C++ native reader for H5. That's the problem, right? We actually didn't think about it that way, right? This is the one thing that we didn't think about ahead. H-file is like as a format, it's like a really good. Somebody's already like solved this problem. It has Bloom filter. It's like a really solid, well-tested B-tree like encoding that is really optimized for point lookup. So we used it. Yeah, we either will write a C++ reader for the format, or we will fork the format. It's not. We already do our own log format and stabilize. So this is not very new, uncharted territory for us.
Something along where you spoke about CDC, is Hudi generating CDC or is consuming CDC?
Both.
Okay.
You can do both.
So with that, we have a lot of struggles like CDC formatting, so the normal comma separated values. There's not
Okay.
It's not super like stating is well defined, and it's really hard to say it's well handled because of the lack of standardization on the index.
Sorry, are you talking about CSV or CDC?
CDC.
When you say so, okay, can you repeat the question? Then I don't follow.
Say we're using a CDC file produced by say Amazon TMS.
Okay.
Or standards were just like G or I.
Sure, sure.
How do you think we can kind of make that format better to handle schema changes, or even know what the schema is in CDC5? We've had a lot of struggles with it. Setting up a table, coding with its schema, and then adding it to CDC files.
Yeah. Okay, this is a good question too. So, okay, so for Zoom, the question is, when you do streaming, like essentially incremental CDC from a database, and you have CDC files, how do you do schema evolution, or how do you know what the new data files are? Right? So this problem is a little bit like on top of a layer like Hudi, right? If you look at this is what a streaming, like a schema registry from Confluent or one of these schema registries do solve. If you're dealing with streaming data, you need to have some contract between your producers and consumers in terms of what they really change. So there's, I don't know, like having like, so I've been at LinkedIn before and like also like, you know, did the whole like Avro based producer consumer schema evolution thing at Uber as well. So based on all that, and then I spent some years at Confluent as well. So what I can tell is this whole schema evolution using in SQL, where you do like alter table rename and all, that's like fine. But when you're dealing with streaming data, nobody stops the stream and like lets you issue alter command, right? So you need to really get like really disciplined around like producer consumers and use some kind of schema registry and have people agree to some kind of schema evolution rules. And I think maybe like Balaji, you can take this to, you do this in production. So what do you guys do? Sorry to throw you.
Yeah. Maybe we look at it like you have a contract. We can operate the schema as we don't have and we try to don't want the schema that we should go now more responsible and
I do have a technical solution for you though, specifically for Debezium. I don't know if DMS has it, but it's not built out. If you guys are interested, happy to like write up a Jira for you. So Debezium, for example, gives you a separate schema topic or something where it sends the DDLs to. So you can block on that. And until like you need to build some logic in your ingest where you need to say there's events coming in, right? I've seen a new transaction number and you need to block on the other schema topic to until you like kind of go past that. You have to be like really sure that no schema changes happen before you consume a change record, right? This is what you do. Like a lot of systems, like, you know, Golden Gate, I was in like part of the Golden Gate that team as well. I think, I don't know, like, I think a lot of database do it in different ways, right? So you need to have some other metadata stream. So if DMS can generate you that, then we need to build some extra logic. I'll go beyond, right? So a lot of people, what they ask for is end-to-end CDC. I have like RDBMS, 100 tables. I'm updating transactionally, like, you know, like a subset of tables at given point in time. Can you take that and apply that transactionally to like the same 100 tables on the data lake? That way, when I query the data lake, it's like a consistent snapshot of the upstream database, not a consistent snapshot of this thing. So let's, again, I don't need to be very critical. All this stuff that we are doing, generally, we have a long way to go to reach like database levels of like consistency and all. There's like a lot of talk right now around this. But if we can build a system like that, where we can transactionally replicate an entire database server, that is the like way I would approach something like that.
we want that
Yeah. But it's just only coming up more and more. Like it's generally for us, we're like, you know, we will be like super happy to enable like an RSE from you guys and build it, and like that'll be awesome. But
we want all of those internet flows. We don't want everything to be fine. Like we want to have, is there a possibility of having every single result inside of this serialization?
Yeah, the question is, why do essentially why do I have to do pre-combined? Can't I store every version of the data? Correct.
Yes, but also have an incremental intra-transactional timestamps for each.
So, okay, so essentially, if there are like, and you still want to update the table. Okay, so you're talking more like a SCD2 type kind of thing, right? So yeah, so there's two ways to do it, right? One is just like an append only data model, but you push all the merge costs to the you need to compute the latest version of the table. The problem for something like pre-combine is that if we allow 2 rows, then finally we need to sort of still figure out all of the indexing, all the keys. We need to make sure this all goes to the same thing. So typically people have built like a initial table where you do the append only model, and then you build a materialized table by building like an incremental ETL downstream from it. That's what I've seen people do mostly. But the pre-combine exists to make sure that for that you have that stream, you have the primary key enforced. Because that's what I've seen too as well, which is people do care about the primary key as well.
On the same line, would it make sense to introduce like a custom or simple functionality? So like say, for example, we do have an append log with the same primary key with some new value.
Yeah.
Let's say the most functionality is not supposed to read this, but instead add 2 values of the column of the primary key and introduce a new row.
Correct. You can do that today, right? But I think what's being asked is slightly different. Essentially, we want commits of, okay, let's take a state of a table, right? Right now, there's no duplicates. Primary keys are intact. Now you get a bunch, like a new batch stream of updates where there are like repetition of record keys. Essentially, what's being asked is you need to classify this somehow into break it up into a bunch of transactions and then apply them such that, each transaction you have all these different updates, right? Let's say key 1, it gets updated 2 times in the record stream. I think we need 2 versions of the table essentially, right? That is what I'm saying. You could still do that today by writing a Spark job that can split it and write it 5 times. That's kind of still you can do that today if you really wanted to. But the thing that I think Harsha mentioned, which is you can choose not to overwrite, but merge it. And maybe you keep a same record key, you change the data model a little bit, you keep the same record key, but you keep history within the record. That's something that you can do, but it does, most people do a log for this kind of thing where they actually for more operational needs than actually not some of this stuff, right? Which is well, I mean, your Kafka data is going to go, retention is going to run out at some point, then you need some log to go back to. So most people end up append only. Then Hudi has this nice incremental query. You can just do an incremental query, and then you can build a downstream representation. That's what you've seen most people do. This kind of lines up a little bit with this whole bronze, silver, gold thing. So you can go all the way to the silver thing with
And then the final part of that, as a person who's never really used can you explain a little bit how Flink ties together with Hudi in the sense of architecture or?
Yeah. So I would say Flink has a lot of impedance match with Hudi in a sense that Flink treats everything as a streaming source. So it has really nice a way. So for example, there's Hudi, there's something called Hudi commit sequence number. It's basically Kafka offsets. That way we can actually within a single Hudi commit, we can actually process that. We have an order within that commit to be able to process that record by record if you have to. These sort of things typically Spark anyway does processes commits as batches anyway, right? So there's a little bit of that. The other good part is Flink's state management is really good. So Flink can be a really good solid index implementation and just use Hudi as a sync. For example, the RocksDB state in Flink is way more solid and easier to operate and performant than let's say Spark, right? So a lot of people use Flink CDC, and there's actually a lot of Hudi in China with like Flink this way, because we have like a Flink state backend. So we talked about many options here, right? Like the Bloom index, all this stuff. We support those in Flink, but as well, people use Flink's native indexing and then the RocksDB state and actually do like near real time CDC into Hudi tables. So Hudi is like really good match there.
So for a HiveSync tool, in documentation, it is written that it's preferable to run in a command line or else in a separate JVM. Why is it so? Like,
sorry, can you come again? What tool? Sorry.
HiveSync.
HiveSync tool. It says it's better to run it in a command line.
Command line or else separate JVM rather than including in your Hudi job itself. Spark app.
Okay. I'm not sure if that's because of this potentially conflicting with the bundles. The bundles in Hudi, like they do package like the sync part as well. So it could be something related to that.
Okay.
I'm not entirely sure. You can just like post this on Slack and I think we can take a look at it.
Yeah, sure.
Right. Thank you. You had one more.
I have one more. The final one is the SLS. We've had a lot of, when we go to load a table, we typically load each batch each time with a particular transaction. And we're talking about like a 30-second SLA for accumulating changes. Is Hudi there? We just have that configuration, or what is your expectations around the commit?
Yeah. So when it says 30-second, I don't mean it in like a job, right? Obviously, if you have 1 MB and you update right now, it will obviously finish within 30 seconds, right? So that's not, so my point was more like for like what I was making there is for like a tough workload, like let's say random updates across like a very large table, can we do like a 30-second update? Like that's kind of like where I was trying to go with a reasonable amount of compute. Those are all the stars, asterisks there, right? Like obviously you can crank up like 1,500 node Spark cluster and you can just like write to like, but that's like, you know, ridiculously over provisioning it, which by the way, you can't anyway do with like a lot of warehouses, right? So this model is still super flexible where you can scale it out based on the amount of compute that you want to burn, right? And you just need to be careful about one thing, which is your file group size, because like if you're doing, let's say copy on write, or like, you know, that's basically the single task time in Spark. So you're not going to beat that. And then there's like some indexing overhead, right? And then we need to do one pre-combine and shuffle, like if you're doing CDC. So this DAG for a complex workload like that, with a reasonable amount of compute, can it actually finish in 30 seconds? That's kind of what I meant. What I think today will happen is will still be like really fast and generally across most update heavy workloads. The update only workloads are actually very easy. That's why I don't talk about it. It's like writing a Parquet file into a folder, right? And then doing a bunch of things around it. It's not that hard. You can actually use anything for it. The mutable workloads is where like most of these struggles will be, right? Because they dirty the metadata faster. You need to have multiple versions of the file. You need to think about event time, arrival time, like all this complexity. There, I think record index is one part of the problem, which is we've not had like a really good solution out there for when, let's say UUID keys, right? And then across like a very large table, and it can go, the updates can go to any partition. It's a very hard, like needle in a haystack kind of problem. There, I think we'll struggle unless you like really over provision it to ridiculous levels. But we are hoping the record index will like bring it down to like really good levels right now. That's what we think. That is the generally for databases too. Random writes are the hardest workload, right? Any database benchmark, if you go look at it, you look at sequential write, random write, you'll see that random write like suffers. So that's, I think, where we are. I think, and just to be clear, just so that I'm being like, you know, just technically factually accurate. We do have like really good update performance.
I think you're recording.
Hey, Vinoth.
All right.
Can you hear me?
Yeah.
This is Siva here. To answer the last, someone asked the question about HiveSync, right? it's kind of the content was misinterpreted. What we have actually meant is for actual writes along with data source or Delta streamer, you can set some configs and get your Hive sync done. If it's preferable to run it as a standalone, we have other options. That's what we have meant in our site.
Okay, sounds good. Thanks for the quick call. All right, this was fun. Thank you so much.